Welcome to Module 51 in this series of lectures on statistical quality assurance and statistical process improvement. This is the second lecture on the choice and use and data analysis for fractional factorial studies. And in this module, we're going to talk about the choice and use of half of a 2 to the p factorial. The issues that one must address if one is going to use a fraction of a 2 to the p factorial, and this kind of notation is common. To say we'll use a 2 to the p minus q fractional factorial. That means one uses a fraction 1 over 2 to the q out of all possible 2 to the p combinations of levels of the factors. The issues to be addressed are to, first of all, how to rationally choose which combinations to get data for. The second is to determine the corresponding pattern of aliasing, confounding, confusion, loss of information that is associated with that fractional factorial. And then thirdly, how to do data analysis. In this module, we're going to address these questions first of all for half fractions, and then in subsequent modules we'll consider quarter fractions, eighth fractions, and so on, that is, smaller fractions of a full 2 to the p factorial study. So to begin, let's talk about choice of a half of 2 to the p combinations of p factors each at 2 levels. To make a choice of what we're going to call the standard half fraction, here's what you do. You write out signs, plus minus signs, for specifying all possible combinations of all but one of the factors, p minus one of them, and then multiply those signs together for a given combination of the first p minus 1 factors as if they were plus and minus ones to arrive at a corresponding level to use for the last factor, the pth factor. Here's an example. Here's choice of a half fraction of a full 2 to the 4 factorial in the factors a, b, c, and d. One begins over here on the left side by writing out all possible combinations of plus and minus signs, specifying levels of, or combinations of levels of factors a, b, and c. I've actually written these out in Yates standard order, if you will, truth table fashion: minus plus, minus plus, minus plus, minus plus, minus minus plus plus, minus minus plus plus, and so on. It's not absolutely necessary you do that, but it's probably easier to organize things and make sure you've got everything listed if you do use this kind of truth table order. And then the point is that if I think of a minus 1 times a minus 1 times a minus 1, I can get a minus 1. If I thought of plus 1 times minus 1 times minus 1, I'd get a plus 1, and so on. That is, I make this column up as a product of the first 3 columns, and I use it to specify the level of the last factor, the 4th factor, factor d. And so if I read across, for example, this first column, I see that A is low, B is low, C is low, and D is low. That's combination 1 of a 2 to the 4th factorial. If I read across the second row, I see A high, B and C low, D high, That's combination AD of a full factorial in 4 factors. You can follow it through for the rest of these, and what I've got listed here then are 8 out of 16 possible combinations of 2 levels of each of 4 factors. And this is our standard half fraction of a 2 to the 4th. Here's another example taken from a ASQC technical supplement published in 1985. Ronald Snee discussed a factor, a experiment where each of 5 factors had 2 levels. Discussed a half fraction of that. The factors and their levels, there was A, B, C, D, and E, each with low and high levels. This was a chemical experiment. There was a well-defined response variable. There was some kind of a color index. And in Snee's study, he wanted to use a half fraction. The particular half fraction that he used led to these combinations, and the listener is encouraged to write out all combinations of A, B, C, and D, and then do the multiplications to get the corresponding level of factor E. And in fact, what then gets is half of all 32 combinations of 2 levels of each of the 5 factors. Snee used the standard recommendation. He got a standard half fraction of a 2 to the 5th. That's how we're going to suggest that one makes a half fraction experimental plan. The question then is, if one does that, what is one left with in terms of patterns of ambiguities and confounding, aliasing, confusion of effects if one uses this kind of a method to make the half fraction. The way that we're going to work that out or figure that out is to use a very clever little method of formal multiplication, beginning from a so-called generator that represents the way in which the half fraction is chosen. So the generator for a standard half fraction is this. One writes the name of the last factor and says, well, it's indistinguishable from, it's equivalent to, and then writes the product of the names of the first p minus 1 factors. One then operates on that generator according to rules of multiplication that says any letter times I produces that same letter, any letter times itself produces I, and one then works from the generator to understand what is confused with, what is aliased with, what is indistinguishable from what. Here's an example. Yeah, let's take a hypothetical situation where I have 3 factors, each at 2 levels, and I want to make a half fraction. Well, the generator then is levels of factor C are chosen as products of signs for factors A and B. That means that the C main effect is aliased with, is confounded with the AB 2-factor interaction. This is the so-called generator for the plan because it says how levels of factor C are chosen. If I take that generator and multiply through by the name of the factor that's on the left. I'll have c times c on the left. C times c is I. I'll have a, b, and c on the right. And this is the so-called defining relation for the experimental plan. One of these strings of letters separated by arrows is going to be called the defining relation if what we've got on the left side is simply I. What this relationship says is that the three-factor interaction is aliased with, is confounded with, is indistinguishable from whatever I is standing for, and actually I stands for the grand mean in this method of formal multiplication. Ultimately, what that says is that one can estimate, or one can learn from a half fraction only the grand mean plus the value of the ABC two-factor interaction. One cannot learn the grand mean alone, nor the ABC three-factor interaction alone. Those effects are aliased. They are confounded. They are absolutely inseparable. They're indistinguishable. If one takes this defining relation and multiplies through by any set of letters of interest, one can see what is aliased with that corresponding effect. So if I start with I being equivalent to A, B, and C, I multiply through by A. I get A on the left side. A by A is I by B times C. I times B is B, so I've got A on the left, BC on the right. I have A being indistinguishable, being aliased with the BC two-factor interaction, and C being aliased with the AB two-factor interaction by the same logic. So for this hypothetical half fraction of a 2 cubed, there is the whole alias structure, and what we end up understanding is that factorial effects are aliased in 4 pairs. And the technical meaning here is that one can't learn the B main effect or the AC two-factor interaction. What one can learn is the sum of those things, and that makes some sense. If I've only got 4 out of 8 possible combinations studied, I certainly shouldn't be able to resolve more than 4 different quantities from data taken from such a study. The hypothetical half fraction of a 2 to the 4th had the generator D aliased with A, B, and C because levels of factor D were made as products of signs for levels of A, B, and C. Multiplying through by D, I get I aliased with A, B, C, D. That is the defining relation. As I say, this is the generator. This thing says how the thing was set up in the first place. And then if I take this defining relation and multiply both sides by A and B, I've got AB on the left, I'll have CD on the right, and we see that in this context, the AB two-factor interaction is aliased with, is indistinguishable from the CD two-factor interaction. In Snee's half fraction of a 2 to the 5th, he began with factor E, getting levels that were defined by products of signs for A, B, C, and D. So he had E equivalent to A, B, C, D as a generator, multiplying through both sides of that by E, one has that for a defining relation, and then starting from that, for example, multiplying both sides by AB, one sees that the AB two-factor interaction in Sneeze study was aliased with a CDE three-factor interaction. In Sneeze study, instead of having to look at 32 different combinations of levels of A, B, C, D, and E, you only looked at 16. It ultimately, when one goes to do data analysis, one has 16 pairs of indistinguishable to the fifth factorial effects. One can learn about the sums, about 16 different sums, not the individual 32 components that make up those sums.